So in this topic, or in this section, we'll be discussing graphical approximations to differential equations. The main takeaway from this section will be learning how to graph slope fields. It's a little monotonous and a little cumbersome, but what they're trying to get you to understand is just how the differential equation looks graphically. So just to review, we've been dealing with dy dx, the derivative of your function that they give you. The important part here is saying rather than try to represent this information in a three-dimensional graph, a slope field is a special type of graph to represent the slope at several xy combinations. So the key here is this. You'll basically it's like graphing, when you were graphing in Algebra 1 or Algebra 2, you basically would get a bunch of xy points and try to graph the graph out. But in this case, you'll be graphing the slopes. Like, you'll be getting the value for the slopes. So it'll show you where it's, a positive slope or a negative slope or a really, really large slope, like if it, so, and then you'll have to discern what it sort of looks like from there. So here, example 5 and 6 found in the previous topic, where we solved the differential equation here, right? And we ended up getting the solution of y equals negative 1/2 x minus 3/2. If you haven't seen the solution for that, refer to the previous video. So there they gave us a particular solution of y of 1 equals negative 2. And then so for that solution, our slope field, or our diagram solution for our differential equation would be this. So then you would see that if you see the graph here, right? You see that the solution that we got, negative 1/2 x minus 3/2, is this highlighted line, right? Because our point 1, negative 2, that's our point here, and our slope is negative 1/2. So it goes up 1 over 2, up 1 over 2. So that's your line there, specifically for that, initial condition. Now, for the other solutions, right? You see that there's all these lines kind of coming in. They basically were plugging in other points, essentially. And so basically you would essentially plug in, you could plug in, we plugged in 1, negative 2. You could plug in, if you wanted, 1, negative 1, 1, 0, 1, 1, 0, 1, negative 1, 1, negative 2, 1, so that would give you, what that would do is give you that solution, and then you would be able to graph it, and that's where they're getting these slope fields, essentially. As you're investigating these graphical methods, think about how slope fields and isoclines can be used in science. In physics, you'd study the variety of forces, most notably gravity, electromagnetism. Would you be able to model the strength and direction of these forces with the slope field? Can you predict or approximate where an object will travel based on the isoclines. For weather, winds can be modeled using slope fields. So those are the conceptual ways, of looking at things. So that was just a high level kind of view of looking at it. So here, this is just going over the details of what a slope field is, right? The idea behind a slope field in isoclines is that for a differential equation of the form y prime equals f of xy, if a solution curve goes through a point x naught, y naught, then the equation gives the slope of the tangent line to the solution curve at that point, right? So basically, at that point, x naught, y naught, if you plug it into your solution or your differential equation, then you get a slope for that. A slope field, sometimes called a direction field, is a graphical representation of the rate of change across all values of x and y. So as we know, the first derivative is always the slope of the curve. So it gives you an idea of the rate of change of the graph. To build a slope field, draw little line segments at points of a rectangular grid to illustrate the tangent line. So, you're not going to be able to do all these accurately, because sometimes it's just, there's too many points. You can't graph all these points, right? For this example here, they kind of give you a good way of looking at things, right? Consider, this equation here, right? When both variables are positive or negative, right? If they're both positive, then they're positive, right? So if they're both positive, then the slope will be positive. So you know that in this quadrant and this quadrant, slope will be positive. And so that means that slope will at least be, going in this direction. And you see that here. It may not be completely horizontal, but nor vertical. It'll probably be asymptotic, right? So here, and then you see when each variable approaches 0, the slope approaches 0. So that makes sense, right? Because as it it can never get close to 0 because it's you're going to have dy over y equals dx over x, and then it's ln of y equals ln of x plus c. So then it's e to the y. You're going to raise e to both sides. Then you get e to the ln of y is y, e to the ln of x is x, and then this is plus c, so it's times. So it's c e to the ln of x, which is just x. So it's y equals c times x, which is your solution. And then in this solution, you'd basically plug in values for x and y, right? So here, if x and y are super large, then your slope is going to get closer and closer to just being vertical, right? And if it's like, same thing on this side. And then if one, if both values are large in magnitude, then the slope is steep. And then on the alternative side, right? Same thing. Yeah. So it's a unique way of looking at it. You didn't necessarily graph everything out like you normally would, but you basically you took care of each, case, right? Or each way that you would be able to plug in values. If both values are, if both are positive, then the slope is positive. If both are large, then the slope is steep. When each variable approaches 0, the slope approaches 0. So it just gives you a way of thinking about the problem instead of having to graph it completely. So the slope field corresponding to the differential equation y prime equals f of x is the collection of line segments with slope f of xy drawn at all points xy of the plane. If xy is not defined at a particular point, draw a vertical line segment. So yeah, basically all that's saying is it corresponds to this differential equation. Like the slope field corresponds to this differential equation through this collection of line segments with that slope drawn at that point that they give you. So if you cannot draw a full slope field because it has infinitely many line segments, you must choose a grid of points and draw only the corresponding segments. Yeah, so there's cases where you could have a bunch of line segments, then you choose a grid of points. And then, yeah, for your exam, some calculators have this application. Those need to be disabled on the IB exams. I don't know if they check for those or not, but yeah. So, we need to draw a slope field for this differential equation here on this grid. Basically, the grid here is that. Actually, what I'm going to do is pull up Paint. Okay, so for this example, we are going to, I'm just going to show the solution and just go over it. Even in the solution, it's already says it's highly unlikely you're going to get a question like this, but I just want to go over the thought process, because you do need to understand, I guess, the derivation of it. So let's see. I'll write the function here. dy dx equals negative y times 1 plus xy all over 1 minus xy. And so here, for example, we're going on the range of x is between negative 4 and 4, and y is between negative 2 and 2. So here, for example, they plug in, negative 4, negative 2, which is this, and they get a slope of negative 2.17. So hence you need to draw a line segment through negative 4, negative 2 with an approximate slope of that. So negative 4, negative 2, that's here. I mean, it doesn't matter, the angle at which you do it, but as long as you know it's negative, right? That is a negative slope, that's a decreasing slope. You would need to do that sort of at each point, right? On this grid. You don't have to get too granular, right? So it doesn't really help you here, but it's just kind of showing you kind of where it could be going, right? It could be kind of doing one of these things, right? As we get more and more granular, based on what you're seeing, right? But you would have to plug in more points for that. So it is kind of monotonous, but I just want you to see kind of what that means, right? And the whole point, the whole idea behind it is that the differential equation that you're getting is equal to the slope. That's that property that we had, right here, right? If a solution curve goes through a point, then the equation gives the slope of the tangent line to the solution curve at that point. So, yeah, right here, m equals y prime of x equals f of x is 0 sub y sub 0. So that's the whole idea behind, trying to understand the concepts here, is understanding, the slope. You're getting the slope when you're dealing with these things. Here they have, I guess you guys use this software called GeoGebra. It's a combination of geometry and algebra. Okay. So here, it's just, you're moving the point around, right? And this tool basically draws it for you. So, yeah. So you would kind of, it gives you an idea of, this is a mere manual process. I'm not going to do all that, but anyways, just, gives you an idea. So, of course, drawing a slope field by hand is time consuming, and the one in the previous example is not really dense enough to give us a sketch or solution. So, technology, for example, GeoGebra, can be used to draw a slope field. This gives you a lot better of an idea of what the slope fields are doing. You see, kind of what we had gone over here, right? You see you see how it's changing right here. It's all negative, and then it sort of changes. Here it's becoming more vertical, then it becomes more positive, and then it goes back to being negative. Here it's kind of doing this thing here, and then here it's kind of curving over, and then here it comes back to being positive. So yeah. So yeah. So here, this is a good way of thinking about it. You can think of these as rivers with a current, right? If you were to drop a leaf at a specific starting point, where would it go in a river if that has a current? It's not necessarily going the path of the river. It's going the way the river current goes. So by mapping the currents, you can get a good idea of where it would land. So the same applies to slope fields. Okay. So example 2, using the slope fields above, it gets a solution curve to the differential equation with the initial condition of 0, 2, and another one at 0, negative 1, right? So let's just go ahead and bring back our graph, right? So at 0, 2, should that be here, right? And then 0, negative 1, so I'll line that up there. And then 0, negative 1 is here. I think all they're wanting you to do is kind of give them a general idea of what the slope would be doing, right? Just literally following the fields, Not entirely sure what's going on here. I think it's doing something like this. So let's see. Let's see here. Yeah, exactly. I was doing that. I mean, it's kind of the same. It's, I mean, literally you can line it up kind of, right? That's all they want. They want you to, using the slope field, sketch the solution curve, and it's saying a solution curve, right? It doesn't have to be, there's multiple ones, right? With the initial condition here and the initial condition there. And so there's multiple ways to do it, but generally they're following that direction, and you'll see kind of, right? So pretty straightforward. Don't have to overthink anything there. Draw some more solution curves for the differential equation. There you go. That's kind of what it looks like. You would, you see, you're literally essentially just following the path of the slope fields, and so this is what it would look like if you drew more, more more possible solution curves. Just getting used to, the weirdness of, okay, well, this was going this way and this was going this way, but then here you see there was kind of a change in the slope, so there's like new information you kind of have to figure out there. Okay. Sketch the solution curve of the differential equation dy dx that passes through the point 1, 1. Right? So we have 1, 1 here, right? So my idea would probably be it's something right around there. Let's see what they have. There you go. Lines up pretty closely, right? Pretty straightforward. It's just following the slope fields. I'm not doing anything crazy, but literally I'm just following the slope fields that they've provided us with. Okay. And we're not going to go over isoclines. They're not going to be included on the exam. You're welcome to go over those.